Welcome to the third episode of the quantum computing series. In this video, we will be talking about qubits and some examples of physical systems that serve as qubits. The bit is the most basic unit of information in classical computing. It can take values of either zeros or ones, and their state is governed by the laws of classical physics. But as processors get smaller and smaller, quantum phenomena start to dictate how these quantum bits, or qubits, work. In previous videos, we have mentioned that qubits can be in a superposition of states. That means that they can take the state 0 or 1 at the same time, whereas bits can only take one value at a time. This weird notation is called the Dirac notation, and is the standard notation for representing a state in quantum mechanics. The general state of a qubit can be represented by a linear combination of states. Alpha and beta are complex numbers, and if we square them, we get the probability of getting each state. The states 0 and 1 are also known as the computational basis. So, how do we actually know the final state of a qubit? This is not as straightforward as it seems. We need to measure the qubit multiple times, as each time the result could be different. Once we have repeated this process many times, we will be able to determine the probability amplitudes alpha and beta. For example, imagine we flip a quantum coin. Up until we open our hand and check the coin, we won't be able to know whether it's heads or tails, right? So we can say that the coin is in a superposition of both states, and the act of opening the hand and observing the coin makes it collapse to one specific state. We repeat this 100 times, or maybe 1,000 times, to arrive at the conclusion that there's a 50% probability of flipping tails and a 50% probability of flipping heads. The equation describing the state of our quantum coin would be this. If we squared alpha or beta, we could get the probability of getting heads or tails respectively. Qubits are very strange, I know. The truth is that they are very difficult to understand because their behavior contradicts our day-to-day classical experience. However, many experiments have verified their existence, and they can actually be made in many ways. For example, let's take a photon. Photons are light particles that can be polarized. When we polarize light, we basically change the direction of the wave. So when a photon is in a certain direction, we can treat it as the state 0. Change its direction, and voila, we get the state 1. Now, let's imagine the position of an electron in an atom. In the atomic model, electrons can be in different orbits, and we can move them to different orbits by shining light on them for a long time. So we can take an electron in the first orbit as the state 0, and if it's in the second orbit, then it would be the state 1. And here's the cool part. If we shine light for a specific amount of time, the electron will be in the middle of these two orbits, and hence it will be in a superposition of states. These are examples of physical systems that can be used as qubits. But why are these qubits so hyped? Well, if we put a lot of qubits together and manipulate them as we desire, we can perform computations a lot faster than classical computers can. So if you want to know how to manipulate these states of these qubits, stay tuned because in our next video, we'll be talking about quantum gates.